So in this section we're going to continue using the derivatives to figure out things about functions, and in particular we're going to talk about Rolle's theorem and the mean value theorem. Now we actually don't know what Rolle looked like, so we'll just draw a little stick figure guy here for him in a nice little wig he probably wore like Leibniz and Newton. And it turns out that Rolle actually really hated calculus. He several times tried to prove it was all wrong, that you got bad results, that it just couldn't possibly be true. But eventually he started to like it, and he proved a good theorem that we use in calculus now called Rolle's theorem. So Rolle's theorem tells us that if you have f, a continuous function, on a closed interval a to b, and it's differentiable on that open interval, a to b, then if f of a equals f of b, then there's at least one number c in the interval so that the derivative at c is equal to 0. Now let's draw a picture to think about what this all means. So first of all, a thing to note is that we have a continuous function, and what continuous tells us is that there's going to be no breaks in our graph. We also know that our function is going to be differentiable, and differentiable just tells us that there's going to be no corners in our graph either. The last thing to note is graphically f of a equals f of b. So graphically what we have here is we have a, and we have a value here at f of a, and we have b, and we know that these occur at the same level. That is, f of a and f of b occur at the same height, and in between what we need to draw is we need to draw a function that's continuous and differentiable. So as I'm going along here, I'm not allowed any breaks, I'm not allowed any corners. It should look a lot smoother than what I'm drawing here, and I know I need to get back here where I started. And what Rolle's theorem tells me is that, well, if I'm going to do this, if I'm going to go from the point here at a all the way over to the point here at b, at some point in between, there must be some places where I have a slope of 0. And in this case, in this graph, we can see that there's a lot of them. There are several places in between where I have a slope of 0. Now, what we could do is we could draw another picture from a to b, and we could see, well, maybe I just try to go up this way. Well, in order to get back down to b, I have to cross a place with slope 0. You know, I could just go levelly across, but in that case, I have slope 0 all the time. Since there's no breaks and no corners, I have to have a slope of 0 somewhere. So a question we might be faced with is, does Rolle's theorem apply to the following functions? So we want to look at our function here, g of x, which is a nice rational function, and we have itself in an interval from -1 to 3, and there are three things we need to check. We need to say, is this function continuous? Is it differentiable? And if we put those endpoints into the function, do we get the same value out? Well, let's go through and look at this. First of all, is this function continuous? Nope. Because if we try to take g of 2, we're going to get a number divided by 0, so this function is not continuous. Okay, so Rolle's theorem does not apply. Let's look at another example. So now we've got another function here on the interval -1 to 1. I know that this function is nice and continuous. However, this function h is not differentiable at 0. So again, no, Rolle's theorem won't apply to this function since it's not differentiable. We can even draw a quick picture to see that even though this function is nice and continuous, that h prime of t is never going to be equal to 0. It's because of this darn corner here that stops us from having a place where the slope is equal to 0. Okay, so let's look at another example. Here we have f of x. Now, this is a good function. One, it's continuous because it's a polynomial. We also know it's going to be differentiable as it's just a nice polynomial function. We can find its derivative and it works. There's no corners, no breaks, nothing bad. And the last thing to check for Rolle's theorem is we need to check, if I put 0 into this function, do I get the same answer as if I put 3 in? Well, what we can do is we can say, well, f of 0, let's see if we run through it, gets 0. F of 3 is equal to, well, -9 squared plus 9 equals 0. So this means yes, Rolle's theorem applies. And we're good to go. This means that there is going to be a place where our derivative is going to equal 0 somewhere between 0 and 3. So just to reiterate, whenever we're faced with a function, we want to check, first of all, is it continuous? Yep. Differentiable? Yep. Are both endpoints equal to the same value? Yep. So this means Rolle's theorem will apply. And so then what we can do is we can find everywhere where it's true. So we can find the c value so that the derivative is equal to 0. In this case, the derivative of our function at c is going to be negative 2c plus 3. And we want to know where this is equal to 0. So we simply solve this equation, and we end up with c is equal to 3 halves. So this is the location where our derivative is equal to 0. And we could even graph this and look at it. So the next important theorem we want to learn about is really the most important theorem in this section, called the mean value theorem. And if you look at it, it looks like I circled it in purple. So what the mean value theorem tells us, if we have a function that's continuous on a closed interval, so we got this idea of continuous again, differentiable on an open interval, then there exists a number c in the interval so that the derivative at c is equal to this quantity over here. And we want to remember, what are these quantities really telling us? What we want to remember is that this quantity on the left here is really our instantaneous rate of change at c. That's our slope, that's our speed, that's what we're doing in the moment. And over on the other side, what we have is we have our average rate of change on an interval. This is our average between our endpoints. And so sometimes this is best to see using a graph. So for this function, what we want to think about is well, first of all, it's continuous in a closed interval. So that means we have a and b. These are going to be points on our graph. And so we can just fill them in. This is at f of a, this is at f of b. So unlike Rolle's theorem, they don't need to be at the same level. They can be anywhere they want. Now since this function is continuous and differentiable, we have to go from a over to b in a nice manner. No real breaks in our graph, no corners in our graph. It just should look nice and smooth. And so things we can do is we can calculate, for example, f of b minus f of a all over b minus a, which we remember is just going to be the slope of this line between these 2 points. And what the mean value theorem is telling us is it says that there is going to be a point along this curve somewhere, call it c, that if we were to draw the tangent line at this point here, that these two lines should be parallel. That is, the slope of the secant line, the average slope, should be the same as the slope of some line at some point. So we have to achieve our average value. So the mean value theorem tells us we achieve our average rate. A way to think about this is to think that suppose you drove 60 miles in 1 hour. That means at some point along your journey, no matter how fast you were going, how slow you were going, whatever, there was some time when you were going exactly 60 miles an hour. So in order to make use of the mean value theorem, we need to check 2 things. We need to make sure our function is continuous, and we need to make sure it's differentiable, and then we can figure out how to use it. So let's try out the mean value theorem on the following functions. So let's look at this first function here, h of x is equal to x plus 1 over x on the interval negative 1 to 2. Well, the problem with this is this function is not continuous at 0, so MVT does not apply. Alright, so that's a pretty easy problem. So here let's try a slightly more interesting function, f of x equals x squared on the interval negative 2 to 1. Well, first of all, 1, it's going to be continuous because it's a polynomial. Second, well, it's going to be differentiable. We can definitely take the derivative of this function again because it's the polynomial, so these both work really well in the interval. So the last thing to do is now to set this up and see what we're trying to figure out here. So what the mean value theorem is telling us is that there has to be a point where our equation here, the derivative at c, is equal to f of b minus f of a. So what we can set up is we can set up f of b minus f of a all over b minus a. And in this case, a is equal to negative 2 and b is equal to 1. So we're going to substitute these numbers into our functions. We take f of 1 minus f of negative 2 all over 1 minus a negative 2. And arithmetic 1 squared minus negative 2 squared all over, I think that's 3. And what do we end up with? Negative 1. And so what the MVT says is it says that negative 1 is equal to the derivative of our function at some point, which in this case, if we take the derivative is 2c, And so we solve. We find that c is equal to negative 1/2. So at negative 1/2 is the place where we achieve our average slope. And here what we have is we have a nice little picture of this again. So the red graph is our parabola, is x squared, and we can see we've got our points on our graph here from -2 up to 1. And so our secant line, or the slope between these 2 points, the average slope is -1, and we get an actual slope of -1 right along here at -0.5. So this is where our average slope is achieved. So let's do one more, just because we can. So again, quickly, this is going to be continuous because it's a polynomial, and also it's going to be differentiable because it's a polynomial. And so next what we need to do is we need to compute the last part, which says what we need to take, in this case, g of b minus g of a over b minus a. So from up here, our interval, we know that a is going to be -1 and b is going to be equal to 1. So this means we need to compute g of 1 minus g of -1 all over 1 minus -1. I'm going to skip a few steps here, but this is going to be 3 minus a -3 over 2, which leaves us just with a slope of 3. So this is our average slope between these 2 points. And now we want to figure out, well, where did we achieve this average? So we take and we say, well, we want to know where does 3 equal our derivative of our function. And the derivative of our function at c is going to be 3c squared plus 2. And now what we need to do is we need to solve. So if we solve this, what we end up with is we end up with, by subtracting 2 from both sides, we end up with 1 is equal to 3c squared, which means 1/3 is equal to c squared, which means c is equal to plus or minus the square root of 1 over 3. And so these are going to be our answers because they both are on that interval between -1 and 1. So we actually end up with 2 places here that satisfy the theorem. There's 2 places on our graph that have the average slope. So visually what we can think is, in red I've got my function g of x here, and I've got my endpoints here, my a and my b, and the purple line indicates my average slope between the 2 points. And so we can see what algebraically lets us happen is we can find these 2 points here at the negative square root of 1 over 3 and here at the positive square root of 1 over 3. These are the places where we actually achieve our average slope. We achieve our average speed, our average whatever, at these 2 places. So with the mean value theorem, you have to remember it is totally possible to get multiple places where you get your average. And these would be kind of difficult actually to visually estimate, but thanks to algebra we can pin them down very exactly. So as always, remember to post a question, remember to do your video quiz, and try your problems, and I'll see you in class.